to protect yourself from threatening skeletons. And yeah, over to you, Jonathan.
Great, thank you for the
And we've
introduction.
started recording, so it's all good.
Okay, yes, thank you for the invitation to speak. So I'm happy to talk about this padded decomposition problem. So this talk is going to be based on several papers. The main result, of course, is this padded decomposition result with Arnold Filzer. Although I'll spend a good amount of the talk also talking about this technical tool that's very important, the buffered cop decomposition, which we developed in a series of earlier papers with Shenji, Hung, Lazar, Shai, and Kwong. Okay. So the focus of today's talk is this padded decomposition problem. And here the goal is you're given some undirected graph, edge-weighted graph. We want to partition the vertices of this graph into clusters such that every cluster has small diameter, and nearby vertices get clustered together with some good probability, let's say. This turns out to have many applications. I won't really talk about them in this talk. But the formal definition of this padded decomposition is as follows. We say that a graph has a beta delta padded decomposition if we're aiming to cluster the graph into pieces of diameter at most delta. And here's the second condition that talks about the guarantee that nearby vertices should get clustered close together. We want to guarantee that every radius gamma ball gets cut with probability at most beta times gamma divided by delta. By cut, I mean there are vertices that belong to two different clusters. So with probability at least 1 minus beta times gamma by delta, this entire radius gamma ball is contained within some cluster. The important parameter is this beta, of course, and we say that the graph has padding parameter beta if we can construct these beta delta padded decompositions for any choice of delta.
So just to be clear, this probability is coming from the stochasticity of the partitioning, right?
Yes, yeah, good, yeah, correct. Yeah, so we couldn't hope to get something like that. So if we wanted to say like deterministically every ball doesn't get cut, then you just wind up with like one giant cluster or something like that. So yeah, so we have some randomness that we have like a distribution over partitions or over these clusters. And this is the probability over that randomness. Good. Okay, so just to explain like where this gamma divided by delta term is coming from, I want to just like give this example of the path graph, which will appear throughout this talk. So if you have the graph that is just the path, very long path, there's not much you can do. Basically, like you have to cut if you want to cut this into chunks of diameter delta. Like all you can do is basically like cut every delta edges, and then maybe wiggle the whole construction a bit to make it random. So maybe you have some random offset, and then you just cut every delta edges. So this means like if you have an unweighted path, every edge gets cut with probability exactly 1 by delta, let's say. And so a ball of radius gamma gets cut, let's say a ball of diameter gamma gets cut with probability exactly gamma divided by delta. Okay, if you look at the radius gamma, you have like maybe a factor 2, I guess. So this beta parameter governs like how decomposable is your graph relative to like the ideal case, which is the path. Okay. And this notion of padded decomposition was formally introduced by Bartal in the 90s. Some ideas of this were present earlier, and Bartal showed that every n-vertex graph has padding parameter log n. And moreover, there are some graphs like these constant degree high girth graphs for which this log n padding parameter is actually tight. You can't do better. So Bartal was motivated by this study of embedding graphs into trees with low expected distortion. But some related ideas had been studied earlier for like these flow cut gaps in the multi-commodity regime. And this padded decomposition has basically become an important parameter for a bunch of approximation algorithms and metric embeddings. Oftentimes, the
Just
quality
another
of
question.
Oh, sorry.
This commodity flow thing, does it shouldn't it require directed graphs, or does it work even on undirected graphs?
So I think what I've tried to write here is for undirected graphs for the uniform, like multi-commodity max flow min cut problem. So I think for directed graphs, the padded decomposition doesn't say much, although I'm not so familiar with the directed setting.
I see.
And in the tightness case, you said constant degree high girth graph. I thought are two examples of the expanders.
Yeah, I think you can also go through. You can also prove that it's like expanders are also hard.
Okay, but
think
when you said the high girth graph, like what kind of graph did you have in mind?
So I think if you have sorry, I'm forgetting the argument off the top of my head, or like the exact statements.
That's okay. That's okay. I just
yes.
thought okay,
maybe expanders.
Okay. Okay.
Yeah. So sorry. I think there exists some graphs like that have, let's say, like 3n edges and girth at least log n, and then you say
well, those I would call expanding probably.
Sure. Sure.
Okay. Yeah, that's
sure.
good. Okay. Yeah. I mean, if you
sorry. Yeah. This is yeah. That's all I meant.
Yeah.
I didn't want to like directly use this expander.
That's okay.
Yes. Sure. Good. Okay. Yeah. So for expander graphs, this is tight log n. But we would like to do better than log n padding parameter, because in a lot of applications, like the quality of the solution is directly governed by the size of this padding parameter. And so a natural thing to look at are these MinorFree graphs. Okay, so a graph minor is some graph that's obtained by like deleting edges or vertices and contracting edges. So here's like the simple picture of this graph G, and then if you contract all of the edges that are highlighted by the same color and delete all the uncolored vertices, then you get this K4 complete graph on on 4 vertices. But this G, the graph G that I've drawn is planar, so of course it excludes a K5 minor. Okay, so in this talk, we're going to be looking at KR MinorFree graphs for constant R, or you should imagine, I think, that R is something smaller than N. And then we ask, okay, in this MinorFree graph, what sort of padding parameter can we get? So MinorFree graphs are a natural thing to study. For example, so of course, like Robertson and Seymour famously showed that any graph class that's closed under minors excludes some minor, some KR minor for a constant R. And yeah, they generalize planar graphs and other interesting graph classes. So the first padded decomposition for MinorFree graphs was constructed by Klein, Plotkin, and Rao. I'll note this is like 93, even before Bartal like formally defined this padded decomposition.
I had one question.
Yes.
So is it appropriate to view this KPR result as like, a literature belonging to this family of pattern decompositions because they output exactly one decomposition, right? I mean, they do not have a distribution or decompositions. So
right, yeah. So I think if you yeah, so there are, and certainly there are earlier works that also output like deterministic partitions. So yeah, I agree, but I think it's fairly easy to get like the randomized version from what was written in KPR. So it's
okay.
I'm just editing them here.
Thank you.
Great. Yes. Good. So they showed this like padding parameter, which is constant for any constant r. And specifically their dependence on r was r cubed. So meanwhile, the lower bound is just this like log r, which is sort of trivial from the fact that any n vertex graph excludes a k n plus 1 as a minor. And Bartal showed that there are these expander graphs that have that have padding parameter at least n plus 1. So we have like this this log r lower bound in terms of the padding. And then it was an open question to like try to close the gap between these two values, so that first, like Vakhtarian and Talwar were able to improve like basically the KPR analysis or something very similar to KPR analysis to R squared. And there's this totally different approach by Abraham, Gavwal, Gupta, Newman, and Talwar later on that gets O of R padding. So there's still this gap. In various like special classes of MinorFree graphs, people were able to show that there's this log of the parameter of interest padding, for example, like bounded genus, bounded path width, and then very recently for bounded tree width. You're able to get log padding, and in this paper with Arnold earlier, well, I guess last year, we were able to show that general MinorFree graphs have padding parameter log r. Okay. So before I talk to you about the proof, I'm going to introduce a slightly different object, which is going to be easier to draw in the slides, and it's how we take a detour through this sparse cover in order to construct padded decomposition. Okay, so let's talk about sparse cover. Here we have a set of clusters that are no longer disjoint. So padded decomposition requires like this disjoint partition of clusters, and now we allow some clusters to overlap. Again, we require all of our clusters to have diameter at most delta. And our guarantee is not that every small enough ball is in a cluster with good probability. We say that now we allow overlap, and we guarantee that every ball is contained in some cluster. So specifically, we say that every ball of radius delta divided by 10 is contained in one of our clusters in this sparse cover. The parameter 10 is arbitrary. I actually should have like written this as a parameter. We can get some interesting trade-offs, but for the sake of this talk, we're just going to look at the case when we care about balls that have like delta divided by some constant, and we want to preserve these balls. Okay, and the measure of quality of sparse cover is this parameter that I'll often denote by tau, called the sparsity. And the guarantee is that any vertex in your graph should be contained in at most tau clusters. Okay, and again, I'll just use this notation that graph has like a tau sparse cover if it has tau delta sparse cover for all choices of this parameter delta. Okay, quickly, let's look at again this example on the line. So if you have,
Question is when you say you want to in the padding you had this gamma, right, or beta?
Yes.
Yeah. So is that related to the tau 10?
Good. Yes. So if you had set gamma is equal to 10 in this definition of pattern decomposition, you'd get this result. Let's say for constant beta, that every ball of radius like delta divided by 10 is cut with probability at most like 1/2 or something like this. So that like with at least constant probability, a sufficiently small ball is preserved. Let's say like a ball delta divided by beta times 10 or something like that is preserved. Yes. Good. Yeah, and I'm just like using this 10 just to avoid notation clutter in the slides, but yeah, really we should get some larger trade-off. Right. Yeah. So maybe to that point, there's this like easy relationship between sparse cover and padded decomposition, where if you have a padded decomposition, you can always like sample this padded decomposition a bunch of times, log n times specifically, to get a sparse cover with sparsity, let's say log n. Like so, if say each time you sample from the padded decomposition, you preserve a ball of radius delta divided by 10 with some constant probability. After log n times that you sample, you'll with high probability have some cluster for all of these balls. Good. Okay. So just quickly to say, what does sparse cover look like on the line? Again, this is like the padded decomposition. Like this is the easiest case. What you can do is just let's say you chop up your line into segments of slightly smaller than delta. So this preserves most of the balls of diameter delta divided by 10, except for the gaps between these two these clusters, and so then we can just expand all of the clusters, and we get something like a sparse cover with overlap at most, like where every vertex is contained in at most 2 clusters, let's say. Okay, good. So to get our padded decomposition, we take this detour through sparse cover. So we show that given a sparse cover, we can construct a padded decomposition. Specifically, like if we have a tau delta sparse cover, we can construct a log tau delta padded decomposition. And then we show that MinorFree graphs have sparse cover with polyar sparsity. Good. Okay, and for the rest of this talk, I'm just going to talk about the second theorem, that MinorFree graphs have polyar sparse cover. And the main technical tool that we use is this buffered cop decomposition, which is some tool that we had introduced earlier in some slightly different context. And so I'll say, like, what is this tool? So informally, we want to partition our graph into these like thick paths, where a thick path basically is the shortest path plus some neighborhood around it, some delta neighborhood around it. The path is sometimes called like the skeleton. And so we want to partition G into these thick paths that have like limited interaction with each other. And the paths are all kind of far apart from each other. They have this like buffered property, which informally means that, so let's say like if you have some path vertices on either side of this thick path get separated by distance, at least like delta divided by some constant. Okay, and I will explain very precisely what this means. Okay, so this was something that we used for padded decomposition, but it's also found a number of other applications, I think, since we introduced it. When we were first studying, like coming up with this concept, like we were motivated by distance oracles and tree cover. We found there's some other applications to Steiner point removal, and like embedding into low tree width graphs. Recently, we had some results on embedding string graphs into planar graphs that uses this idea. And my hope is that this is a powerful tool, and that hopefully it will find many more applications in the future. But I think that the formal definition of the buffered cop decomposition can be somewhat intimidating if it's the first time that you're trying to read through one of these papers. So what I want to do in the first part of this talk is to like go through like slowly and motivate the different parts of the definition of this buffered cop decomposition. And at the end of the talk, I'll explain how to use this buffered cop decomposition to get the good sparsity sparse cover. Okay, so for the rest of the talk, first I want to talk about this cop decomposition, which is going to be the motivation for buffered cop decomposition, but without the buffer property. Then I'll talk about how buffered cop decomposition leads to this 2 to the r sparse cover, and then finally the improvements to polynomial on R. Okay, so I want to first review the concept of tree width. So a graph with bounded tree width is just like some graph that looks like a tree in some sense. So we say that tree decomposition of G is a tree of bags. Every bag is a subset of vertices of G. And we have the guarantee that for every edge, U, V, and G, there's some bag in the tree decomposition that contains both U and V. Let's say these green vertices are both have an edge between them, and there's some bag. And then we also have this guarantee that for every vertex in G, the bags containing V form some connected subtree in the tree decomposition. Okay, and the width of the tree decomposition is the maximum size of the bag minus 1. And the tree width of a graph is just the width of the best possible tree decomposition, or the one that minimizes the width. Okay. And so graphs of bounded tree width are often easy in some sense, or algorithmically we can work with them. You can maybe do some like divide and conquer or dynamic programming, just like a tree. But of course, there are many MinorFree graphs that don't have low tree width. Canonical example is this grid, which is precisely the obstacle to tree width. So a square root n by square root n grid has tree width O of square root n. There isn't really all that much you can do other than taking, let's say, the rows of the grid and putting them in some bag, like two adjacent rows go in a bag. You can maybe improve this by constant factors, but for right now, let's just say asymptotically the tree width is O of square root n for a grid. Okay, but a grid is easy to deal with in a different sense. Sure, all of these bags have square root n vertices, but they're kind of well structured. Like these bags are all the union of like two rows of the grid, and each row is like a shortest path in the grid. So this still has some nice structure. So there's this general theorem where we can say for any planar graph, you can partition the vertices into shortest paths such that if you look at the contact graph of these paths, it has tree width constant. So in the grid case, we just have like our partition is just going to be, we take each row as a shortest path that we add to our decomposition. The contact graph is just this path. And so we have like a simple tree decomposition. To my knowledge, this explicit statement doesn't appear in the literature, but it essentially follows from shortest path separator hierarchy with constant holes. Okay. So I want to just like give a couple of examples of how you might partition a graph into the paths this way. So the simplest possible case is this grid that I've shown.
Clarification.
Yes.
Yeah, the shortest path, do you care to bound the length of the shortest paths, or they can be arbitrary?
The shortest paths can have arbitrary length. Well, they're at most the diameter of the graph.
And you want that any two vertices that appear in the shortest path must be okay. So there is use some sort of uniqueness, or like any arbitrary shortest path between two.
Oh, yeah, no unique. This is not a necessarily unique decomposition. This is just saying that there exists some partition of the vertices into shortest paths. There could be many. Like I guess like in the grid case, you could also equivalently take the columns and you'd also.
Yeah, no, I'm thinking particularly about a cycle, right?
Sorry. So following up on that question, like Jonathan, I mean, like the contact graph for like this grid, it's like so structured nicely, like lines out into a path. But like, for example, if I take like, let's say, like, I mean, a different graph, like a maybe three-dimensional grid, or like perhaps even an expander, like, so I guess this shortest path partition, it's kind of like throwing me off. I'm not able to like visualize it very clearly. So for instance, for a 3D grid, what would it look like?
So for three-dimensional grid is doesn't exclude any minors, I believe. You can.
That's right. That's right. Yeah, that contains large minors.
So this is going to. So actually, the way that I've shown this is like specifically for planar graphs, and there's some analog for MinorFree. But it, yes, but in general, like if you have a large clique, I think you can't get something like this.
Okay. Okay. Fair enough. Please continue.
Yes, sure. So just to give some more examples, maybe like the simplest possible case is this grid where you have like this contact graph as this path. Maybe a slightly more complicated example. Here I've just like deleted some of the horizontal edges of the grid. So now like the rows are sort of broken, and that means that we can't get the contact graph to be well, the way I've drawn it, the contact graph of these clusters isn't a path, it's a tree. I suppose if you took the columns, you could actually get a partition into paths where the contact graph is a path. But you could imagine in principle that there are planar graphs where you can't partition into shortest paths where the contact graph is a path. Like you might have to require like this treeness. So these are sort of like some in between of like a grid plus a tree. That's the way I like to think about it.
Yeah, but and it's not increasing your tree width. Like deleting edges is not going to increase your tree width. So.
Deleting edges won't increase the tree width, but it could increase it could change the structure of this contact graph, because maybe if you delete an edge on the shortest path, now you can't decompose like a large chunk of, maybe you can't take a large chunk of your
no, but like look at the two connected components of the shortest path, and you just click, now you have two vertices, and then just triggers do whatever you did there. earlier. Okay, that's kind of a moot point.
I believe this. So this runs into some issue where maybe like suppose you have a let's say like a 3x3 grid or something. Like you have a grid and you just delete the middle edge. Like you can form like these cycles, I think. Yeah. Like.
Right.
But.
Okay. Yes.
Yeah. So basically, deleting edges changes the stratus path structure, and it's kind of unclear what happens.
Okay, so this is not a robust notion. I mean, it's not a downward closed thing.
Yes. Yes.
So I don't know what to think about this. Okay, good, thanks.
Right. Yes. Yeah, it's very specific. And so just to give one last example, when of an example where the contact graph isn't a tree, but you might actually need bounded tree width. This comes from the fact that you can have like pieces of planar graph that sort of like nest within other pieces of planar graph. So like if you have this wheel, basically no matter how you try to partition this into shortest paths, you'll always end up with some sort of cycle in the contact graph. Okay, good. But then the claim is that okay, the contact graph might not be a path, it might not be a tree, but it always can have bounded tree width. It can look sufficiently tree-like. Good. So now we can ask, what about MinorFree? Does such a structure theorem also hold for MinorFree graphs? And unfortunately, the answer is no. And the reason is, look at a grid with one apex vertex. So when this black vertex is just connected to all of the vertices of the grid by a short edge. And now there isn't any way to partition this graph into shortest paths where the contact graph has bounded tree width. The reason is basically that any shortest path of length, any shortest path either contains 2 vertices or it contains 3 vertices and it goes through the black vertex. So all of your path, so eventually what you're going to do is like, okay, you want to partition this graph into shortest paths. Okay, well, one of those paths can use the black apex vertex. And all the other paths just have to have be single edges, basically. They have to have only 2 vertices because we want to partition into shortest paths. We don't want to, these shortest paths aren't allowed to overlap. Okay, so so essentially, no matter how you do this partition into shortest paths, you're going to end up with a large grid, meaning the contact graph has large tree width. But in this case, there also is something like natural to do, which is you take the black apex vertex as one path, maybe, and then take the rows of the grid as the other paths. And so this is kind of natural because each of these rows in the grid is still a shortest path if you ignore the black vertex. So this is a theorem that was like, this construction was originally given by Andrea in the 80s, and then it was interpreted as this structure theorem by Abraham, Goswal, Gupta, Neiman, and Tauer later on. And what they proved is that you can partition G into these, what I'm calling downward shortest paths, such that the contact graph has bounded tree width. And by downward shortest path, I mean, so if a path is in some bag B, let's say we look at this purple path in this bag B, and we delete all of the vertices and bags above this bag B. So if you delete all of this paths that came earlier, like in this order, essentially, and you just look at like everything below you in the tree decomposition. Then the purple path is the shortest path in this graph. So essentially what we do is we imagine iteratively constructing these shortest paths. And the guarantee is that whatever path you create in the current iteration has to be shortest after you've removed everything that came before you. So this is called the COP decomposition. So Andrea originally studied this in terms of cop robber games, and he showed that there's always a winning strategy for a certain number of cops by following along these, by patrolling these downward shortest paths. And then it was,
Yeah.
yeah.
So those were basically called the threateners, right? The downward shortest paths.
So I'll use the word threatener to mean things that are above you and are within distance delta.
Okay.
So yes, so like
close bags, basically, like close bag members, basically.
Sure. Yes, exactly.
Yeah. Okay.
Yeah. So yes, there is the notion of threatening also has this notion of order, and like you only threaten things that are below you, just like these paths are only shortest with respect to things below you. Good. Okay, so let me quickly describe the construction of Andrea, I guess, to, well, yeah, I guess I'll just like flash the animation, but I won't talk about this in detail. It's a very simple algorithm where you just iteratively construct these paths, and you iteratively like draw paths towards the existing previously constructed paths. So you start at some vertex. This is your first path. Okay, now you select another arbitrary vertex. You draw a path towards that old vertex you selected. This is your second path, and clearly this is the shortest path in this graph. After removing the orange, you repeat this. You select another vertex. You draw paths to the previously constructed paths, and these are your next two paths in the decomposition. Okay, at this point now some paths get cut off from the rest of the graph. So like now this orange vertex is no longer visible to this large connected component of G. And so when you select the next vertex and draw paths, you only draw these paths to the paths that you can see. Okay. And Andrea shows that if your graph excludes a KR minor, then you can only see like R squared paths at one time, or otherwise you can build a KR minor. So this is the construction, just like iteratively drawing shortest paths. Good. So let me now talk about the buffer property and how we're going to use this to construct. First, I'll talk about this 2 to the R sparsity bound for sparse cover. So maybe let me introduce this notion of threatener in the context of 2 very simple graphs. So if we want to construct a sparse cover in a path, like we said before, what you can do is partition the paths into clusters of diameter delta, and we have this like property that every cluster is within distance, let's say like delta by 2 of only one cluster to the left of it. So then if you just expand all of the clusters rightward by delta by 2, you get this 2, O of delta sparse cover. And the key property that that we're using to get the sparse cover that says this expansion is safe is that each cluster is within distance delta by 2 of only one cluster in this order. And we call this like the threatening cluster. Okay, we can say something similar for a tree. If you want to construct sparse cover on a tree, what do? You partition your tree into clusters, again, of diameter delta. And now it could be the case that each cluster is within distance of like delta by 2 of many different clusters. But we can say that if you view this as a rooted tree, and you look only at the ancestor clusters, every cluster is close to only one ancestor cluster. Otherwise, you have to walk past these large blobs. Okay, and again, so this is like this, you only have one threatening cluster. And so you can expand every cluster downward by a delta by 2 amount to get a 2, of delta sparse cover in a tree. Okay, and so what we would like is to have this property for general MinorFree graphs. And this is the intuition behind this buffer, why this buffer property is useful for sparse cover. So recall this like very high level intuition is we're going to, the buffered decomposition is going to partition our MinorFree graph into these like thick paths, which are downward shortest paths plus some delta neighborhood. Contact graph has bounded tree width, just like the decomposition. And we have this additional like buffer property that says the paths are well separated. Removing a path separates the 2 halves of your graph by at least like delta divided by some constant, just like trees and paths. Okay, so the building block of the decomposition was these shortest paths. The building block for the buffered decomposition is these thick paths. So I guess want to start by saying that a thick path is easy to deal with in sparse cover. Like if you have a graph which just consists of a shortest path plus a delta neighborhood, it's easy to get a constant delta of delta sparse cover. And the argument is just completely essentially identical to sparse cover on a single path. You find these clusters of radius roughly delta, and then you expand them a bit, and then you use triangle inequality to say each cluster can only be threatened by at most one or 2 clusters when you do this expansion. Okay, so thick paths are easy to deal with. Good. So before talking about the buffer property, like the full definition of buffered decomposition, I want to sort of step through some simpler examples of how when we can define this buffer property. So first, let's imagine we have a decomposition where the contact graph is a path, and I'll talk about what happens when the contact graph is the tree, and then finally when the contact graph is bounded tree width. Okay, so suppose you have a graph with this property that you can partition G into these thick paths. Contact graph is a path. In this case, we're going to define the buffer property as follows. We say that this partition obeys the gamma buffer property if for any 2 thick paths A and B, either they're adjacent or they're separated by distance at least delta by gamma. So in this drawing, like we have like this rectangular grid. Again, there's a very natural partition to these thick paths, I guess by going along the rows. And we have this property that, so suppose we have this property that, let's say this green and this red thick path are not adjacent, and so they're the distance between them is at least delta divided by some gamma. You should think of gamma to be roughly O of R, by the way. Eventually, we're going to get a buffered decomposition where with a gamma buffer property where gamma is equal to the O of R. R is the size of the excluded minor. Okay. So in this case, I claim that constructing a sparse cover is easy. We can construct a sparse cover with sparsity O of gamma. And the algorithm is very simple. You start with these thick paths, then you expand all of them by distance O of delta, and then claim that each vertex after this expansion into thick paths doesn't overlap many of the expanded thick paths. And then within each thick path, you chop it up into bounded diameter components like we discussed previously. Okay, and just to like explain like why we get sparsity O of gamma. Essentially, if you have this gamma buffer property, you have O of gamma threateners. You have O of gamma thick paths that are within distance delta, because every time you walk past one thick path, you have to pay like delta divided by gamma distance. And so after you walk delta distance, you can only have walked past O of gamma things. Every thick path has O of gamma threateners. Okay, this is very similar to what happens if we have a graph that can be partitioned into thick paths where the contact graph is a tree. So how do we define this gamma buffer property? Again, we say that either two thick paths are adjacent, or they're separated by distance at most gamma by delta divided by gamma. But now we have to impose the condition that this only applies when, let's say, when one of the thick paths is an ancestor of the other in this tree. We don't necessarily have any buffer between siblings of sibling paths of this tree. Again, this gamma buffer property suffices because when we construct our sparse cover, we're always growing our thick paths downward. We're always growing downward, and so again, this gamma buffer property in trees is sufficient to show that you have O of gamma threateners. Okay. Of course, our theorem for MinorFree graphs is that G can be partitioned into such a thick paths such that the contact graph has bounded tree width. So we want to define this gamma buffer property similarly to the tree case. So yeah, so if you have a MinorFree graph G that can be partitioned into thick paths where contact graph has bounded tree width, the gamma buffer property is defined as follows. If you have thick paths A and B that aren't adjacent, and additionally A is in some sense like an ancestor of B, the formal definition is like if A is in some ancestor bag of a bag containing B in this tree decomposition, then their distance is at least delta divided by gamma. And so we were able to show that any KR MinorFree graph has such a decomposition where the contact graph has tree width poly R, like R squared, similarly to the COP decomposition. And additionally, it satisfies this gamma buffer property for gamma equals O of R. And this is inspired by this decomposition of Ibrahim, Gabwal, Gupta, Neiman, and Talwar. They essentially achieved something very similar to our buffer property, but only in expectation. We were able to do this deterministically. And this deterministic bound is important for sparse cover. Okay, so what sort of sparse cover do we get from this gamma buffer property in a bounded tree width graph? So we get something that's exponential in R, assuming that the tree width and gamma are both poly R. So for some intuition, like suppose that gamma is 1, like you have this perfect buffer. So if gamma is 1, and then the gamma buffer property says the only ancestors of the thick path B that are within distance delta is everything else in the same bag. So like if you consider this bag, green thick path, if we had gamma equals 1, the only thick paths that would be within distance delta are the purple and the blue thick paths. And so if gamma equals 1, then every thick path would have O of true width threateners. Okay, if gamma equals 2, then basically you can be threatened by anything that's in the same bag as you, or something that was in the same bag as something that was in the same bag as you. So, so the green guy could be threatened by something that's in the same bag as purple, or in the same bag as blue, as well as these guys itself. And so if gamma equals 2, we get something like true width squared threateners. So maybe this suggests some sort of like true width to the gamma bound in the number of threateners. And there's a closer analysis that gives 2 to the r for true width and gamma. That's poly r. This was shown by Arnold. Good. Okay. So this lets us get 2 to the O of r sparse cover. And in the few minutes I have remaining, I want to talk about the improvements to poly r sparse cover. So we have from this COP decomposition 2 to the O of r threateners. And the first thing that you might try is to improve the properties of the buffered COP decomposition directly, so that every vertex has poly r threateners. For example, you could do this by improving the buffer parameter to some absolute constant that's independent of r. Unfortunately, this seems very difficult, and so our bypass is to still work with the same buffered COP decomposition with 2 to the r threateners, but then do divide and conquer on this, as opposed to just carving and like growing all of the paths downward. So the intuition, I think, is easiest from this example where let's try to get poly r plus log n sparse cover. And we can do this by, let's not even use the buffered COP decomposition. Let's just work from the COP decomposition of Andrei right now. So what we can do, we might try to do, and this is kind of hard to illustrate, but the idea is, as opposed to just growing balls downward from every node in the COP decomposition, what we should do is like pick some centroid bag of this COP decomposition. Then we should grow clusters around all of the paths in this centroid bag. Okay, so there's, let's say, O of r squared paths in this bag. So if we grow balls, we've added maybe O of r squared overlap clusters to our sparse cover right now. And then after we do this, we recurse on all of the remaining components. So there's log n levels of this recursion. Each time we're adding, let's say, like r squared, O of r squared, overlapping clusters. Sorry, yeah, there's a typo of this in my slide. I should have said we're aiming at poly r times log n sparse cover. Sorry. Right, but this sketch of like choosing a centroid bag, growing clusters around the bag, and then recursing in all components seems like it would maybe lead to poly r times log n sparse cover. There's two issues here. So first is this doesn't work. you can't just grow a ball around a bag in the tree decomposition, because our COP decomposition is not a decomposition into shortest paths. It's a decomposition into these downward shortest paths. Basically, this means it's only safe to grow balls downward into the graph with which you are a shortest path with respect to. So this is not something that you can do. You can only grow downward. And that means that if you just try to recurse on all of the connected components after removing this ball, not every ball of delta of radius delta by 10 need be covered. Okay, so we have to be a bit more careful about how we do this recursion. I'll skip past this. And then the second technical challenge, of course, is to avoid this log n term. And here's where we have to exploit the buffer property and say that we can select a bunch of far apart bags where we can grow balls around them all at the same time.
By the way, you have about 10 minutes.
Oh, great. Yes. Okay. Thank you. I actually thought I had less time than that. But good.
We are extending everything by 10 minutes, so it's supposed to end now, but it's fine.
Okay, so maybe
we started a little bit late too, so it's okay.
Yes. Okay, so maybe I'll say something about this avoiding the log n term. So we're inspired by this paper on padded decomposition bounded tree width graphs, and so we use some very simple version of this technique. So what are the bags that we should try to grow around instead of the centroid bag? What we want to do is we want to select a set of bags so that that has two properties. Like first, every bag in our COP decomposition should contain at least like one thick path that was marked. So this means that after our rounds, this is going to terminate. And second, we want to say that these bags are all the paths in these bags are all far apart. That this buffer property implies, this O of R buffer property implies that every vertex is threatened by poly R marked paths. So the way we do this is it gets to this greedy algorithm. So you can start with the root of the tree decomposition. Say you mark it. It contains, let's say, this thick path 801, and then you skip past all of the bags that contain 801 until you reach a new bag that doesn't contain this 801 that was marked. And now we mark all of the thick paths in it, and so on. And so basically the buffer property says that anytime you jump between these marked bags, you pay at least delta divided by R distance. And so you can show that any vertex is threatened by O of R bags. Each bag contains R squared paths, and so each vertex gets threatened by R cubed marked paths in each layer of this recursion. Each time you do this, you remove one bag one path, and then you terminate after poly R layers of this recursion. Okay, good. So just to conclude, we showed that MinorFree graphs have part of the 4 sparsity sparse cover, and consequently log R padded decomposition, where R is the size of the excluded minor. And the key tool is this buffered COP decomposition. We did this divide and conquer on the buffered COP decomposition, which is some structural theorem that decomposes a MinorFree graph into these thick paths, where the contact graph is well behaved and tree-like, and the paths are also well separated. Okay, so I've put some open questions here. Some of them are about like getting better guarantees for buffered cop decomposition. So it'd be interesting. I mentioned this before. Could we like directly improve the buffer parameter in buffered cop decomposition to gamma equals constant instead of gamma equals O of R? This would maybe provide like a simpler proof of log R padded decomposition, and hopefully would lead to strong diameter guarantees on sparse cover, or maybe even padded decomposition. So we were able to only construct sparse cover and padded decomposition with weak diameter guarantees, where the distance between vertices is measured with respect to the original graph as opposed to within a cluster. And then there's also this interesting question, I think, about how quickly can we compute this buffered cop decomposition? It's poly time, but it seems like it's maybe some largish poly time, because we have to do a bunch of sequential shortest path computations. And we don't know how to bound the depth of this. Okay. Yeah, I think I'll stop here. Thank you.
Thanks for the great talk. I cannot switch on my video because video sharing is somehow not working, but thank you, Jonathan.
Yeah, thanks for the great talk, man. Yeah, I mean, I had a I had some doubts about like why this buffered cop decomposition even makes sense to like sort of think about, like what is the intuition behind the buffer property, and I think I have an answer now, like, which is great.
Great. I'm glad.
Yeah, what is maybe I should stop the recording. Stop. Okay, now yours.